just really quickly, I want to review the general, not numeric, but just general titration curve from last time. We did a strong titration curve, and we did a strong acid with a strong base, and it looked like this. And we had our equivalence point at what pH? 7. And that will always be the case for a strong. Now, we said we could have started with the base and then added the acid. There's no reason you can't do that. The equivalence point is still the same. It just depends on who's in your flask and who's in your burette. If you start with the acid in the flask and slowly add the base, it will look like this. If you start with the base in the flask and slowly add the acid, it will look like this in general. You start off super acidic, end up super basic, or you start off super basic and end up super acidic. Again, when this is a strong with a strong. Strong acid, strong base. Strong base, strong acid. Any generic questions about this before we move on? All right. So, today, we're going to do a weak with a strong. Now, this is already recorded and online. You can already access it, like not this one from right now. So you'll be able to watch this in 2 different spots, okay? And the way we do this, we're going to use a weak acid with a strong base, but you could use a strong acid with a weak base. It would be done very similarly. So there's going to be 2 types of titrations that are really important for you to know. Strong and weak strong. Can you do weak titrations? Yes. Are we going to care much about them? Nope. We're going to focus on the strong or the strong weak. Okay? So again, if you've watched the videos, you've noticed that we do the same steps over and over and over again. The first step is to identify the major species. So you go, okay, I have acetic acid and I have sodium hydroxide. Okay, so, oopsie. Weak acid, strong base. Now, there are 2 ways to know that acetic acid is weak. One way is that you memorized all of your strong acids and it's not one of them. So it's weak by default. What is another hint in this problem that acetic acid might be a weak acid?
Because of weight?
They gave you the Ka value. So K values, equilibrium constants, are only given for things that go to equilibrium, and weak substances are the only things that go to equilibrium. Notice they don't give you a Kb for sodium hydroxide. Guess why? Because it's a strong base. Strong acids and bases don't have K values. Only your weak species have K values. So the problem actually gives you a little hint that the acetic acid is a weak acid if for some reason you can't remember. Now remember we said acid and a base is an actual chemical reaction. It's a neutralization reaction. And it can be done using the laboratory technique of a titration. So it's still a neutralization reaction, it's just usually done very slowly. Step by step, you slowly add the base to the acid or the acid to the base. Again, the titration is nothing other than the laboratory technique of how you're mixing the acid and the base together. A common reason for doing a titration, not what we're doing right now, but a common reason is to find the concentration of an unknown species. So like you'll know the concentration of one of the species, but you don't know the concentration of the other. So that's a general reason why we do titrations. So the titrant is the thing that's in the burette, and the other substance is in the flask, the Erlenmeyer flask. Acid-base titrations are not the only types of titrations. They're the types we're focused on right now, but you can do redox reactions in these also. Anything where you want to know something's concentration, you can do a titration with it. Again, this chapter is about acids and bases, so we're focusing on acid and base titrations. Would there be any reason to put an acid in the flask and an acid in the burette? No. What's that going to do? Nothing. You're just mixing acids at that point. You're not even having a chemical reaction. You can cause dilution, sure, but you're not going to get any data out of like an acid-acid reaction or a base-base reaction. So let's read the problem. I give you numbers, and then I give you a Ka value for acetic acid. This is acetic acid. And I ask you, A, to determine the initial pH. So it is important when you read the problem that you know who you're determining the initial pH of. Is it the base or is it the acid? So you kind of need to know who's in the flask based on how you read the problem. So my hint to you is when they give you the volume and the molarity of the species, that's usually the thing in the flask. And then when they say it's being titrated with, this is the titrant, meaning that's the thing in your burette. So we're trying to find the pH of the flask. What is the pH of the acid in the flask? So part A is not a titration problem. Part A is a weak acid problem because all you have in part A is the weak acid. They're trying to find the pH of a weak acid only at the beginning. So part A is actually a weak acid problem. This is definitely part A, something that's fair game for your quiz. So, first thing you do, identify major species. Well, in part A, it's just acetic acid, and it's a weak acid. Step 2 is you write out the reaction. Now, it's not really a reaction. It's an equation. So we're going to write out the equation, and it's the weak acid going into equilibrium with its ions. So how do we do that? We write out the weak acid. You add water to it because it's in solution. And equilibrium because it's weak. Hydrogen ion donor. Hydrogen ion acceptor. That's the Bronsted-Lowry definition. So identify major species, write out the equation or reaction if it's a chemical reaction. If it goes to equilibrium, we set up an ice chart and we plug in everything we know. We know this is 0.1. Now water is a liquid, so we don't care about it. And this is 0. Oh, wow, this is H3O plus, excuse me. And then if we have something that goes to equilibrium, you can set up an equilibrium expression. Okay. Oops. Now remember, H3O plus in this class is synonymous with H plus. They mean the same thing. And I know Ka, right? It's given, so I'm going to erase this and replace it with the actual known Ka value. It's given in the problem. It's 1.76 times 10 to the negative 5th. Now, this isn't always true, but when K is given for a weak problem, you usually have to let X equal something. In the times where K is not given, if they're asking you to solve for K, you usually have enough information to plug and chug. You don't have to have X equal anything. But when K is given, it's a good hint like, okay, this is it. Like, this is all I have right now. I don't have anything else I can plug in. So I have to plug in an X because otherwise I can't solve this. There's like nothing else in the problem that's given in part A. So I'm going to let X equal the concentration of hydronium ion at equilibrium. I could have just as easily picked acetate because they're in a 1-to-1 ratio. And again, because this is a 1-to-1 ratio, everything is X then, right? Which is nice. So yes, this is prior to mixing. This is just the weak acid sitting in the flask before you've added any base to it. So I want to know its pH. I want to know the pH of the weak acid before I start adding base to it. So this is 0.100 minus X, right? And now that I have my equilibrium values, I can plug them into my equilibrium expression. And then we always do this to avoid the quadratic, and you always will be able to. We get rid of that minus x because we pretend it's really, really small relative to 0.1. Oops, that's a 0.1, sorry. Okay, and we solve for x. So you multiply both sides by 0.1. And that gets rid of this. Now x times x is x squared, right? So this ends up being 1.76 times 10. Okay, I'm going to unplug this just really quickly. It's like not cooperating. 1.76 times 10 to the negative 6 is what the this is going to be from over here. Okay, but then in order to get rid of the square, you got to square root it. Okay, so you square root it, and if I remember correctly, x is like 0.00132 or something like that. 132 something. So we're not finished, so keep the whole number in your calculator. All right. This is the H3O plus, or the H plus, however you want to look at it, concentration. So can I find pH now? I can, right? pH is opposite the log of H. So pH is opposite the log of 0.00132. Now again, keep the whole number in your calculator. It ends up being like 2 something, I think, right? 2 point. Okay, 2.877, 2.878, 2.876, 2.87 something. Again, if you're off a little bit right here, no biggie. This is the initial pH of the flask of acetic acid. Okay, so you probably don't remember, but I do. When we did the strong acid, strong base titration last class, I think it was HCl and NaOH, the initial pH of that flask was 0.301. That's what it was. You can look back on it. That was the pH. Look at that compared to this. Why do you think that this pH is higher? I mean, it's still acidic, okay, which is good because it's an acid, but it's definitely not as acidic as the other one we did because it's a weak acid. So if it doesn't ionize as extensively, it doesn't produce as much hydrogen ions. And if it doesn't produce as much hydrogen ions, you're not going to get as strong of an acidic pH. So this is a much higher starting pH than our strong. It's still acidic, don't get me wrong. It's just not as acidic because it's a weak acid. Any questions about this part? Because now we're going to get into the crazy stuff. Okay? All right, so that was our starting pH. Now we are going, so A is finished. Now we're going to add 10 milliliters of the titrant. Well, the titrant is sodium hydroxide. That's the species that's in the burette. So just like the strong problem, we're going to have dilution. You're taking two solutions, you're mixing them together, and we're going to dilute them. So this is going to be done the same exact way as the strong right now. So M1V1, M2V2 for the acid. The acid is 0.1. You have 25 milliliters of it. It'll have a new molarity. And now after you add 10 milliliters to 25 milliliters, we have a total of 35 milliliters. So this is for my acid. Then you do it again for your base. Now your base is 0.1. And you've added 10 milliliters of it. It will become diluted when the final volume changes to 35. I'm not sig figging these numbers because I'm not finished. I basically am writing out to where they stop rounding. Okay, so this is diluted, but before they have reacted. Now, we need to write out the equation. Now, this isn't an equation. This is like a legit reaction. So we will do this one time, the full way, and then we will start using the net ionic way. But let's write out the reaction. We have CH3, COOH, acetic acid, reacting with sodium hydroxide. You should be able to predict the products. And a one-way arrow, because this is a reaction. This isn't equilibrium right now. This is assumed to be aqueous because it's in solution. This is assumed to be aqueous. Sodium acetate will be my salt. So that's NaCH3COO. Oops. You can also actually write that as CH3COONA. It means the same thing. Or NaC2H3O2. Salt and water. Alkali metals are always soluble. So sodium's an alkali metal, always soluble. Water's a liquid unless you're told otherwise. Now, here's where you have to be careful. Weak. So in order to break things apart, two things have to be true. One, you have to be aqueous. You are not allowed to break apart liquids, you are not allowed to break apart solids, and you're not allowed to break apart gases. You have to be aqueous. But something else has to be true besides just being aqueous. You have to be a strong electrolyte, meaning you have to ionize extensively. So our strong electrolytes are strong acids, strong bases, and any sort of soluble salts, ionic compounds. This is a weak acid. You are not allowed to ionize it in a net ionic equation, meaning you have to write it like this. Don't touch it. Now, sodium hydroxide is a strong base, so I can totally rip it apart. Now, this is a salt. It's ionic, and it's soluble, so I can rip it apart also. And then I got water. Is a liquid, I don't get to touch it. So in this instance, I only have one spectator ion. It's sodium. So my net ionic looks like this. Which is definitely different looking than our net ionic from our strong titration. What was our net ionic from strong? H plus OH minus makes water. That's not what it looks like when there's a weak species. So when we're doing our ice charts, now I want to point out I'm not going to do an ice chart because we're doing equilibrium. I'm going to do an ice chart to organize our math. Use the net ionic. And even if you want to, when you do strong, you can use the net ionic there. H plus OH minus makes water. That's fine. So this guy's molarity is 0.0714. The hydroxide is 0.02857 because that's sodium hydroxide, right? Acetate is 0, and we don't care about water. Now, remember when we did this for the strong, we didn't have anything on the product side because water, right? That's not the case here, which is what's going to change how we do this problem. So what is nice though is that this is a limiting reactant problem, just like it was in the strong-strong. So you still treat it the same way in terms of a limiting reactant problem. They're reacting in a 1-to-1 ratio. How do you know it's a limiting? I have amounts of both reactants. So whoever you have the least of is your limiting reactant because they're reacting in a 1-to-1 ratio. So I lose all of the hydroxide. And if they're in a 1-to-1 ratio, I lose the same amount of acetic acid. Now, I gain, because it's a 1-to-1 ratio, this amount over here. Whew. Okay. So the whole point, if you don't remember, is we're trying to find the pH right now after we've added some base to the acid. Right now, we know two ways to find pH. If we know H plus, we can find pH because pH is opposite the log of H, or H3O plus, however you want to look at it. Do you see at the end, this E, any H plus ions present? Are any of these H plus ions? No, right? Okay, so that's out. Another way we can find pH is if we know POH, we can work backwards to find pH. But POH requires having OH ions. POH is opposite the log of OH. Do I have OH ions? Oh, no. So until now, those are the only two equations we've used to find pH or POH to get pH. That is not going to work for a weak, strong titration right now. So if you go look on your equation sheet, there is actually another pH equation that I'm about to introduce. And it looks like this. Ooh, hello. So this equation is called the Henderson-Hasselbalch equation. Okay. Kids, for some reason, like to call it the David Hasselhoff equation. I don't know what's up with that, but it's called the Henderson-Hasselbalch equation, and it gives us an alternate route to find pH that we haven't learned yet. Now, this equation right now is the equation for a buffer. We haven't talked about buffers yet. That's okay. It involves finding the pH using the pKa, so a weak species. Ka is a weak species, right? And then taking the log, and then up top is your conjugate, and on the bottom is the weak species. So the A minus means your conjugate, and HA means your weak acid. Weak acid with its conjugate base. All right. So you go back to the problem and you go, so I have Ka, right? So I have that number, it's given. Do I have my weak acid and its conjugate? Well, I don't know. Let's look. This is my weak acid, and this is its conjugate base. So I just plug straight into the Henderson-Hasselbalch equation. So I'll just rewrite the equation on here. pH equals pKa plus the log. Now the conjugate goes on top, so that's acetate. Right, so on your equation sheet, they call this A minus because it could be any conjugate. And then the weak species goes on the bottom, CH3COOH. And we just plug and chug. Now, how do you find pKa? You got to remember that the P literally stands for negative log, right? Because pH is negative log of H. So pKa is negative log of Ka. So pH is negative log, that's what the P stands for, of Ka, 1.76 times 10 to the negative fifth. This was the original Ka given in the problem. Plus the log, and then you have to go back to your ice chart and look at those numbers. My conjugate is 0.02857. My weak is 0.042857 something. Oops. When I do these personally, because I don't love parentheses and stuff, I usually calculate this guy first, this guy second, and then I write them both down and then I add them together. But, I'm not going to tell you that's how you need to do it, but that's just how I do it to avoid messes. So, like this number, the pKa ends up being 4.75 something. And I keep the whole number in my calculator. 4.754, whatever. Plus, and then the log of the other number is like negative 0.176 something. So you divide these and then take the log of it. So if you add them together, you get 4.578-ish. So really, the only two new things of this part is how you write the reaction out. The net ionic doesn't look the same as it does with strong, and how you calculate the pH. I have introduced a new way to calculate pH based on what species are present. The reason we didn't have to use the Henderson-Hasselbalch pH equation and the other problems is because we either had excess H plus or excess OH minus, and boom, you can find pH or POH like that instantly. This isn't as easy because we don't have excess H plus, we don't have excess OH minus. We have set up what's called a buffer. Okay, the neutralization reaction actually caused a buffer to be formed, and we'll talk more about that in detail later. Again, so that's why we use this new equation, and you don't have to memorize it, right? It's on your equation sheet. You just have to recognize when to use it based on what you have left over after they've reacted. Okay, so someone said, how do you lose, this much of, like, I'm assuming you're talking about law of conservation of mass. How do I lose this much here and here, but only gain that much here? Well, the other stuff is going into water, but water doesn't, so like we could figure out water's mass from this, but we aren't going to do molarity of water. So that's why we don't discuss it. But the other part that's missing is the water. We're just not using it for our calculations for pH because water is neutral. All right. I've never heard that phone ring before, so there's that. Okay, so we just finished part B. So now we're going to do it again. So B's done. So this is going to be done the same exact way. Now we're going to add 12.5 milliliters of the titrant, or of the base. So what do? Do the dilution. So we have 0.1 molar acid, 25 milliliters, new molarity. Now, if you have 25 milliliters of acid and 12.5 25 of acid and 12.5 of base, that's a total of 37.5 milliliters of stuff. Now the base is 0.1 also, but we're only adding 12.5 of it right now. Final volume should still be the same because now they're mixed in the same container. So now that they're diluted, we need to react them. Now, I'm going to use this same net ionic. So we're going to start practicing getting good at this. When you have a weak species and you go to write a net ionic, we're trying to kind of cut out the middleman so you can get good at it and be faster. You write the weak species intact, and you add the strong base without its other component. This is sodium hydroxide, but I'm going to write it as hydroxide because it's strong. So the strong species is ionized and the weak one is not. Now, if you look at it like this is a hydrogen ion donor, and it's an acid, right? And this is a hydrogen ion acceptor. So this guy is going to take the hydrogen. So what do you have left? So if you kind of look at it like this, you know, this guy, think of it like the Bronsted-Lowry way. Loses the hydrogen, takes the hydrogen, because HOH is water. Acid, base, salt, water. Acid, base, salt, water. Where's the sodium? Who cares? Doesn't matter. Spectator ion. It's not actually participating in the reaction. So again, what do? Set up your ice chart. And we're not setting it up because it goes to equilibrium. We're setting it up because it's a nice way to organize limiting reactant problems as well as equilibrium problems. How do I know it's limiting reactant? Well, because I gave you amounts of both reactants. Okay, now they're reacting in a 1-to-1 ratio. My hydroxide is still my limiting. I don't have enough of it. Again, they're all 1-to-1 ratios, right? Just make sure you make your product a positive, right? Because you're gaining product while you're losing reactants. And just to kind of clarify, the hydroxide ion concentration isn't really 0, but it's like a really, really, really small number, so we call it 0. Now, let's discuss again. I'm at the end, so how to find pH? Well, if I have H, I can find opposite the log of H, but I don't. If I have OH, I could find opposite the log of OH and then get pH from there, but I don't. So we have this new way with the Henderson-Hasselbalch equation that allows us to find the pH if you have a weak substance with its conjugate present. And that is the Henderson-Hasselbalch equation. pH equals pKa plus the log. The conjugate goes on top, so that's acetate. And the weak acid goes on the bottom. And then you just plug and chug from here. pH equals pKa plus the log There is a reason I specifically did this volume. .033 divided by 0.033 is 1, and the log of 1 is 0. This is a special point in the titration where the pH equals the pKa. And this happens in every weak strong titration at a specific point. So I want to go back. I'm not going to go up there. I'm just going to show you. The acid is 0.1 molar, and we have 25 milliliters of it. The base is also 0.1 molar. So what is my equivalence volume? If they're the same concentration, the volume should be the same, assuming they're reacting in a 1-to-1 ratio, right? So 25 milliliters is my equivalence volume. Equivalence volume is sometimes represented VE, where E means equivalence and V means volume. So 25 milliliters is my equivalence volume. We're not doing 25 milliliters in this one, though. What are we doing? What volume of base in this one? 12.5, right? How is 12.5 related to 25? It's exactly half. This is half equivalence volume or half equivalence point. So all weak strong titrations will have a halfway point. And they do this because the system becomes buffered. All strong weak titrations will have a half equivalence volume. And it's always half of whatever the volume is. And at that point, 100% of the time, pH equals pKa, every time. So if your equivalence volume is 100, your half equivalence point would be 50, and pH would equal pKa at 50. If your if your equivalence volume was 10, your half equivalence point would be 5, and pH would be equal pKa at a volume of 5, every time. And the reason that is because at the half equivalence volume, you have exact amounts of the weak and the conjugate, which always makes that be the log of 1, and it'll go to 0 every time. The math will work out that way, regardless of who your substances are, as long as one is weak and one is strong. So the reason I did this point specifically was because it's the special point of a titration, where pH equals pKa, and that will always happen when you're halfway to the equivalence point by volume. Now I can still calculate it though. I haven't calculated it yet. pH equals pKa. So pH equals, remember P means opposite the log of Ka. What was the pH at the last point? 4.5 something? And now it's 4.7, even though I added more strong base to it. Does anybody know what the point of a buffer is? You don't have to know. I don't expect you to know. The point of a buffer is to resist drastic changes in pH. Did the pH go up by very much? Nope. Guess why? Because it's buffered right now. Now, every buffer has a capacity, meaning there comes a point where you're going to add so much base that there's no more buffer anymore. It's going to keep going. But in some points of a buffer, it can resist very big changes in pH. Even though I'm adding a strong base, the pH didn't go up very basic because this part of the system is buffered. Now, I'm jumping ahead a little bit because you don't really know what a buffer is, but the presence of a weak substance with its conjugate is a buffer. It creates a buffer. And what's interesting is this isn't a buffer problem, but it kind of is, because the acid and the base reaction created the buffer. The buffer is like a byproduct of the neutralization reaction. So yeah, you neutralized, but the neutralization produced the conjugate, which allowed you to form a buffer, which is why we use the buffer equation to calculate the pH and not the other equations. Okay? We're learning a lot right now. I know this is a lot, but let's keep going. We're just going to do the same thing again, but a new point. Now, if you notice, this next point is going to be, I think, 25. So we're going to do the equivalence point, basically, is what this point is. So 10 we just did 12.5. Now we're going to do 25, which we know to be the equivalence point because we just talked about that. So the equivalence point of a weak strong is also a really special point, right? Because we know for the equivalence point of a strong, the pH should be 7 all of the time. No exceptions if they're both strong. So let's try to figure out what it's going to be for a weak strong. Now, I already told you last class it's not going to be 7, right? I said that only is true for strong. So let's discuss it. Well, okay, of course, do the dilution. 0.1 for the acid. You have 25 milliliters of it. It will become diluted and have a new molarity. Now, 25 of the acid and 25 of the base gives us 50 milliliters of stuff. And then the base is 0.1. We have 25 milliliters of it. I mean, it's pretty apparent these are going to come out to be the same number, just like putting them next to each other. So the question is what is that same number? 0.05, I think, for the acid, 0.05 for the base. Again, we're trying to get in the habit of not having to do a full net ionic. So we go, okay, who's my acid? It's a weak acid, so I write it as is. And then I go, okay, who's my base? It's sodium hydroxide. I know it is a strong base, so I'm going to write it as hydroxide. Hydroxide means strong base. Just like H plus or H3O plus means strong acid when it's a reactant, okay? Loses a hydrogen, gains a hydrogen. So CH3, COO minus, and water. HOH is water. Acid, base, salt, water. Where's the sodium? Don't care. Doesn't matter. Spectator on. So again, set up your ice chart to organize your limiting reactant problem. Water is a liquid, so we don't care about it in terms of concentration. No salt until they react. Still a one-way arrow because this is a reaction. This isn't an equilibrium problem right now. So then you go, okay, well, they're both perfectly limiting, so we lose the same amount for both of them. And then we gain that amount over here. And the point of this question is to find the pH. So pH opposite the log of H plus, don't have that. POH opposite the log of OH, don't have that. And then I just taught you this new equation that we got really comfortable with, sort of. But in order to use it, the Henderson-Hasselbalch equation, you have to have a weak substance with its conjugate. Do you? Oh no. The weak acid is gone. It got neutralized. So I cannot use the Henderson-Hasselbalch equation. This is the really hard part. In a weak, strong titration at the equivalence point, actually write this down word for word. In a weak, strong titration, or strong, weak, whatever, at the equivalence point, in a weak, strong titration at the equivalence point, the salt will undergo hydrolysis. We'll talk about why in a second. So I'll repeat it. In a weak, strong titration at the equivalence point only at the equivalence point, the salt will undergo hydrolysis. And the reason that is because all you have at the equivalence point is salt and water. You don't have anything else. Now, why does it happen here and not in a strong? Well, that is because the conjugates of a strong acid or a strong base are weak. So when you do the net ionic, you get H plus plus OH minus makes water. We're not working with any salts over there. When one of your species is weak, though, it produces a pretty strong conjugate, if you remember. Weak species have stronger conjugates. And when I say strong, if this is my acid, this is its conjugate base. So because it's kind of strong, it's just not going to sit in there and mind its own business. It's going to be like, yeah, so I'm a pretty strong base. And so I'm going to be able to here's your salt. This is your salt. That's what's left, right? And water. This guy, conjugate base, right, of the acid, is going to rip a hydrogen away from the water because it's so strong. As a result, it produces hydroxide ions in solution because it ripped the hydrogen off the water. This is called hydrolysis of a salt. Hydrolysis because of the water and the water with the salt. Let me emphasize, this only happens at the equivalence point because all you have are salt and water. This is your salt, and you go, sodium acetate is my salt. This is sodium acetate. It just doesn't have the sodium ion on it because the sodium ion is just like floating around in solution. This is your salt. Here's the hydrolysis part, add water. Okay? Now, the reason I put this as equilibrium instead of a one-way arrow is because this is still weak though, right? It came from a weak acid. I mean, it's a strong conjugate, but it's not like a strong base now. You don't all of a sudden have a strong base. We only know 8 strong bases, and this isn't one of them, okay? But you're putting it with water. This isn't like a reaction, okay? However, this acetate's like, yeah, I'm gonna rip a hydrogen off of you, water, because we're in here together, and I'm like not weak enough to just mind my own business. And so it does. So we do a second ice chart at the equivalence point where we consider the salt in there. We could care less about the water in terms of concentration. And then these are zeros. And then you go, what? How are they zeros? We had acid and base. Oh, no, you don't. You just neutralize them. There's no acid and base in there. You just neutralized them. All you have at the equivalence point of any titration is salt and water. Even strong is salt and water. The problem with this one is the salt is like kind of strong. So it's not going to just like float around. The conjugates of strong acids and strong bases are really weak. So they're just like do, and they don't do anything. So water gets to be in there and be like, oh, I'm fully water. I'm pH 7. This guy's like, yeah, that's not going to happen. Okay. So we have a second ice chart where this is not a limiting reactant problem. This is an equilibrium problem of a weak base. So we have to let X equal something because I don't have any other information right now. So let's let it be hydroxide. And then again, everything is a 1-to-1 ratio. And right, we set up, if this is an equilibrium equation, we're going to set up an equilibrium expression, products over reactants. We don't ever include water. So K equals, you're probably getting really good at this, X squared on the top. And then this is 0.05 minus X, but like I'm going to get rid of the minus X. And this is the next hard part. And then I'll be done with the hard parts. Okay? Did I give you the equilibrium constant for this? I gave you the equilibrium constant for acetic acid, right? This is not acetic acid. This is acetate. It's its conjugate base. You cannot use a Ka value for something that's acting like a base. But there is a way to jump from Ka to Kb, and we haven't done it much, but we're going to do it right now. And it's on your equation sheet. You don't have to memorize it, and it looks like this. Ka times Kb is the water constant, 1 times 10 to the negative 14. So I do know the Ka for acetic acid, so I can plug that in here to get the Kb for its conjugate base. So you take 1.0 times 10 to the negative 14th and you divide by the Ka, which is 1.76 times 10 to the negative 5th, and that will give you your K for this. And it's like 6 point something times 10 to the negative 10. It's like a really small number. Oh, 5.68, sorry, times 10 to the negative 10. 5.68. And again, I could not use the Ka value because what I'm working with right now is not an acid. It's a conjugate base, so it's a base, in other words. Now I can solve, right? Multiply both sides by 0.05, take the square root, and x equals, I'm going to kind of let you do that. I know you can multiply in square root, 5.33 times 10 to the negative 6. The Ka value is 1.76 times 10 to the negative 5th because that's the Ka of acetic acid. And this is acetate, which is the conjugate of acetic acid. It's given up in the beginning of the problem. Well, what's nice is that this is OH. So we can find POH now because X is OH. So POH is opposite the log of 5.33 times 10 to the negative 6. And then you take that number and subtract it from 14, and that's how you get the pH. And so the pH ends up being 8.727. And remember, we're at our equivalence point. And we don't have a pH of 7, which I told you was going to happen. We have a pH of 8.727. So the question becomes is, why isn't it 7? And there's two reasons that are both related. When this conjugate is strong enough to yank a hydrogen away from the water, it produces hydroxide ions. What are hydroxide ions? Basic. Is that right? That's one way to look at it. The cheap, easy way is that this is the titration of a weak acid and a strong base. So guess who wins? The base, because it's stronger. So we will have a basic pH if the base is strong while the acid is weak at the equivalence point. Which then means, what if this was a weak base and a strong acid? The equivalence point would be acidic, lower than 7 at the equivalence point, because that strong species just overpowers at that point. And this all has to do with what kind of salt was produced. This is a conjugate base, so it's a basic salt, which gives us a basic salt gives us a basic pH at the equivalence point. All we have is salt and water. Water's neutral, so if your salt's basic, your pH is going to be basic. Man, this stuff is hard, but I'm hoping it kind of is making sense of why things worked out the way they worked out. We have one more to do, and this one you're going to be like, ah, okay, because we're going to have excess base in there. All right, so we're going to go so we started at the beginning, we add a little bit of base, hit the equivalence point. Now we're going to keep adding more base. Okay, so we're going to move past the equivalence point. And I think this volume, if I look back, is 35 milliliters of base at the last one that I'm asking you to do. So this one's done, 35 milliliters. So starts off all the same. Do the dilution, set up your reaction, set up your ice chart, and react them. So the dilution is, the acid is 0.1 molar. You have 25 milliliters of it. It'll have a new molarity once they mix. Now, if this is 25 of acid and... This sounds like math. It is math. Are you saying they gotta do math? Yep. And chemistry? Tons. So they should pay attention to my class. They should. Okay. I have a question about cheer. Yeah. All right, so the final volume when you take 35 of the base and 25 of the acid is 60, right? That's our final volume. So this is our acid. Oh my gosh. So now I need to do this for the base, which was 0.1 molar also. However, now we've added 35 milliliters of it to the acid. Again, they should both have the same final volume because now they're both in the same container. That container is your Erlenmeyer flask. So the molarity of the acid when it's been diluted, but before it's reacted, is 4.166666666. Okay. And the base is 0.0583 something. Okay. So we diluted them. Now we're going to react them. Again, weak acid I leave alone. Strong base I write as hydroxide and omit whoever it is, LiOH, KOH, NaOH, CSOH, doesn't matter. The weak acid loses its hydrogen. Oh, yep, sorry. To make salt. And the base takes it to neutralize and make water, HOH. Set up your ice chart again. Again, this is not equilibrium, but it'll help us look at our limiting reactant problem. And it's limiting reactant because we have amounts of both reactants. Now, in this case, acetic acid is my limiting reactant because I have less of it. They're in a 1-to-1 ratio, so I will lose all of the acetic acid. And I will lose the same amount of hydroxide because they're in a 1-to-1 ratio. But I will gain that amount over here. So this is 0. I mean, it's not technically 0, but it's a number pretty close to 0. Okay. What equation do I use to find pH? Okay, actually, let me stop there. Can I use the Henderson-Hasselbalch equation? You have to have the weak substance present with its conjugate. Can I use that equation? No. Okay. Do I hydrolyze the salt like I just did in the last part? No. Why? Well, one, because I told you so. I said you only do that at the equivalence point, and we're not at the equivalence point. Also, you only do that because you only had salt. You didn't have anything else. I straight up have excess hydroxide. Find POH. You got excess hydroxide in there, sweet. Let's find the POH. That's going to overpower any sort of salt. I don't care who the salt is. POH is opposite the log of OH. Wow. And you get a POH of like 1.778. So the pH is just 14 minus that number. So the pH is 12.222. So this one was like nice because I had hydroxide. So now that we have a couple of data points, I want to build this titration curve. We'll do our initial pH and then 10 milliliters and then 12.5 and then 25 and then 35 because those are all the different calculations we did. So I'm going to set up my curve the same way where you have your x-axis and your y-axis. Oh my God. Ah! I'll do it down here. Oh, remember that the y-axis is your pH scale. So 0 to 14, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then I'm going to do this like 5, 10, 15, 20, 25, 30, 35, 40-ish. And then I'm just going to plot all of my data points. So my first initial pH was 2.7 or something like that. The very beginning was 2.7. 10. Oops, sorry, that was 5. Okay. And then my next one I did at 10 milliliters. And at 10 milliliters, it was like 4.5. 1, 2, 3, 4.5-ish. And then 12.5 was the next one I did because that was the half equivalence point. And that like only went up to like 4.7-ish. And then the equivalence point was 25, and that was at 8 something. And then the last one I did was 35, and that was like 12 something. So this isn't the best wording, but for some reason I always kind of use it. I always consider like weak strong curves like kind of lazy. Like the ones in the strong are like really, really steep in lots of places. Like it's like down and then up and then over. This one's like, and then, ooh, no, see? So like comes here. Okay. Like I call it like lazy because the other one again is like really steep in most spots. This right here is your buffer region. Okay? Like the pH is just like a gradual increase. And the other one it was like this. Okay, it was like vroom. Okay? This one's like okay? We've got a basic pH, 8 point whatever. And again, that happened because our salt was basic. We don't have a super, super strong starting point because our acid is weak. However, it does approach a really strong basic pH because it's a strong base. Okay, so titration curves of weaker species with stronger species just don't have as much sharpness. Now, I could have just as easily started with the strong base and ended with the weak acid. All that would have done is I would have started off really basic, and then it would have kind of like done this, and then it would have leveled out not at that low of a pH because it was a weak acid. However, still a basic equivalence point, okay?